This is a pre-recorded session for IAT 3403, and in this recording we're going to be covering Descriptive Statistics Part 1, and in this recording it's going to be going over just a few pages 2 and 3 in the handout, and basically what we're going to be talking about is just some data collection basics. We're going to talk about the data collection sheets and how you would go about doing that. And the reason why we talk about these things is in the problems that we do throughout the semester, throughout this course, we talk about we use word problems to go through the concepts. And the data is already collected for you. It will tell you that you have an average and a standard deviation, and you have sample sizes, and it gives you the descriptive stats off of that. But it doesn't go into how that data was collected. So we're going to talk briefly about that. Then we're going to talk real quickly about what are a couple of tools, and there's quite a few tools that could cause us to use the different things that we're going to be doing this semester. But what are some of the things that would cause you to do some of the types of hypothesis testing that we're going to look at. So basically covering pages 2 and 3 in the handout. So let's start off by talking about data collection basics. The first thing you need to understand is the difference between a population and a sample. When you talk about populations, these are values that we very rarely know, nor should we know. Unless the population size is extremely small, there's really no reason to ever actually measure the population data. Now in some instances, there are cases that require us to collect population type data because of regulatory issues. If you are doing measurements on certain types of medical type devices, types of prescription drugs, things for the aircraft industry, things that are extremely regulated, sometimes we have to take measures like that. There's also cases like in the nuclear industry where that's highly regulated, where you have to be able to constantly account for all of the energy and all of the nuclear fuel that you have for those types of processes. So other than that, in most real-world type examples, you never have population data. What you have is you have sample data, and from that sample you draw inferences about the population. And so when you take sample data, it is typically as accurate as when you do population data, because if you measure population data on large samples, the concept of errors come into play, where people get bored with what they're doing, they get tired with the process, and so they start making errors in the process of measuring population type samples. So our population type data, so the sample data is or can be as effective as knowing the population data. When we are taking sample data, the data needs to be representative, random, stable, and properly stratified. When we talk about representative, that means that the sample that you are taking is representative of the population. One of the things that should be used that can be used to describe this is when you talk about election polls. Where do you take your sample data if you're trying to determine who should be a Republican nominee or a Democratic nominee? The way that it's set up in many of the states is that you can't participate in when you're electing your Democrat and your Republican representatives. You have to only vote in one of those parties. You can't vote in both. So an appropriate representative sample for a Republican primary would be to sample only Republican registered voters. Same thing for a Democrat. In order to do a good representative sample for a Democrat primary would be to only sample Democrat voters. If I were to want to sample product for or sample people's views on advertising for specific shows, people need to understand what is the target audience of the specific shows. If you were looking back in the day when I was growing up, if you were looking at MTV, you wouldn't be taking samples or understanding the interest of people that are 40 and over. That was very largely teenager age through their 30s. So understanding what the targeted age group is a very important thing. If I wanted to make desks for people that are in elementary school, I would want to go and sample, take average heights of elementary school students. I wouldn't go and measure junior high school students. So I think you understand the concept of representative samples. Also, random sampling is very important. And basically, just a quick definition of random sampling means that any one sample out of the population or any one item out of the population has an equal chance of being chosen to be measured as any other item in the population. That is truly random sampling. If you were to want to know how big the desks should be, how tall they should have the desk of students at Southern Poly, they shouldn't just go and measure the people that are on the basketball team. Again, there's some overlap between the concepts between representative sampling and random sampling, right? Random sampling would mean that every person in the Southern Polytechnic State University or the Kennesaw State University student body should have an equal chance of being chosen so that you would get a good representative sample and a good random sample for the type of estimation that you're making. The data should also be stable. And basically what stable data means is that the data is not going to change when you measure the performance of that item from one time period to the next. There could be some minor fluctuations in that. Like if you measure somebody's heart rate, it will not be constant. It will not be stable, and that has to be understood. It changes throughout the day, and it's still not an alarming process. As long as it stays between, say, 55 and 180 beats per minute, that could be very natural, very okay measures of your heart rate, just depending on what type of activity that you're doing normally throughout the day. So, but stable would be if you were measuring the dimensions of parts, you have to understand, could those parts change from time to time? One of the products that I used to work with was plastics, and a lot of plastics are hygroscopic. In other words, they can absorb moisture. And if you do packaging based on weight counts, if you absorb moisture, that's something that has to be very fully understood. That would not be a stable process based on weight measures if you have hygroscopic parts. If it's not affected by the environment, it can be extremely stable, and that's another dimension of data that you need to understand. Also, data needs to be properly stratified. And when you talk about proper stratification, if you were collecting parts from an assembly line or from a manufacturing process and you had 3 different machines that were making the same parts, you would need to note in your data collection which machine that the individual parts came off of, so that you could know if there were to be problems or inappropriate amounts of variation, you would know which machine it came off of. If you don't stratify your data, it's very difficult to know when you have known causes of issues when you're doing control charting and typical problem solving and that type of work. So proper stratification of your data is very important. One of the things that I do when I'm stratifying my data, I make sure that I understand the online student performance versus the in-class student performance or the hybrid students' performances, and so that I can make sure that there's not a difference, a large amount of difference in between the way that I'm presenting the material to those different student groups. Okay. Let's talk about data collection plans. I'm not going to go too deep into this, but when you're doing data collection plans, you should establish your data collection goals. And in doing that, you should clarify the purpose of the data collection and identify what data to collect. And that goes back into your random data, representative data, stable data, and properly stratified data. You also want to develop operational definitions and procedures. So when we talk about operational definitions are simply explaining measures to the point that any person, even if they're not super familiar with the process, they could come in and measure things the exact same way as anybody else. Okay? If I were to want to measure my weight, or the weight of an individual. I would weigh all of those people in the morning, or I would weigh all of those people at lunchtime. And if I did it at lunchtime, would it be before lunch or after they ate their lunch? Or if I did it in the evening? Because the human body can gain weight throughout the day. And then while they're sleeping, they lose that weight off. So it's typically the same most mornings, all things being equal. It will be the same at lunch, all things being equal, then the same in the evening. But you have to be able to properly define with an operational definition and write procedures describing exactly how and when those measures are to be made. And with that, you establish a sampling plan. You also want to ensure data consistency and stability. You do that by testing and validating the measurement system, doing gauge R&R. It's not an aspect of this class to go into that, but gauge R&R is extremely important. You have to be able to ensure your measurement capability so that you can effectively prove a before and after type of measurement. And if you do have stability in your data, you have to make sure that you have stability in your measurement system. If I were to say that I want to get 10% improvement with a process or with a product, and if I have more than 10% variability in my measurement system, then there's no way that I would ever effectively be able to prove whether I have significantly improved that product or process. So the understanding and knowing the amount of variation that you have in your measurement system is an extremely important piece, and that's something that we don't have time to go through in this class. Also, data collection and monitor consistency. You need to train your data collectors. You need to pilot the process and make adjustments as needed to make sure that you do have a good, stable measurement system, that your operational definitions work, and that your data collection plans and your data collection sheets, that they actually work the way that you need them to. You will also want to then go through and collect the data, and then you monitor data accuracy and consistency. Make sure that your gauges continue to perform accurately. Make sure that your data collectors continue to use the appropriate sheets and that they continue to use the appropriate methodologies that you laid out in your operational definition. So that in general is what a data collection plan should ensure if it is developed properly. Then you have data collection sheets that come out of that. When you make a data collection sheet, you need to be able to include these four things. First, the purpose. State what you are trying to do with the data that's being collected. Two, you need to have data stratification capability, dividing them into groups based on key characteristics such as the time it was collected, the location or the condition, and a lot of different things like that. Number three, you need to have the operational definition and procedures well defined. You need to define exactly how you will collect and record the data, including the unit of measure that you're going to be using. For instance, if you were to look at this particular part here and how we are measuring the width of this part, would you measure it across this way, or would you measure it from this tip over to this tip? All right, so you could have your greatest outside dimension, or you could have your symmetrical outside dimension for this part. That's something you would need to clearly define in your operational definition exactly how you do that. Do you measure it on the outside tip of the jaws, or do you put it all the way up in the jaws? If you understand how these calipers are made, there's actually some indentions when you get on up into the jaws of that device. So you would need to clearly make sure that the operators clearly know that they don't need to get up into this indented part of the jaws of the caliper device. So that's the concept of operational definition. And also, as far as data collection sheets, you need to make sure that your notes state who, what, when, and where, whenever it's appropriate, so that you can clearly, again, stratify your data and have good data collection notes. All right, let's move on down to what causes us to use the tools that we will be studying this semester. Just one of the tools that we might use would be the cause and effect diagram. Other names for this tool, you have the fishbone diagram. As you can see, this does look somewhat like a fishbone type skeletal object. And this is also known as the Ishikawa diagram, which is named such after the person that developed this tool, Kaoru Ishikawa. So basically what we need to know when we use these tools is you have key performance measures. Whenever you have key performance measures that are below the standards, that would cause you to go out and do a lot of data collection. That would cause you to go out and develop descriptive statistics of those parts. With the cause and effect diagram, the way that this works, this would be a problem or an issue that you are experiencing here in the head of the fish. So in this case, you have late TSB delivery. This is a software update type issue. Once you know what your problem is, then you develop categories, for instance, people, processes, quality, and management. There are things known as the 4 M's. There's the 4 D's, a lot of different ways that you can come up with these categories. These are good ones to start with if you don't have any other reason to develop different categories. So then if you're talking about why would you have a late software repair, as far as process goes, you could have the wrong scope. You could end up changing the scope as you're going through. You could have the handoff not done on time. You could have milestones not understood. You could have proprietary information. You could have the line of balance not properly developed. A lot of different things around the process that you could come up with. As far as the people, you could be using remote contractors. You could have low capacity. You could have people that aren't cross-trained with the different softwares associated with this TSB. So you would continue to do that. So you use these categories. You just come up with and brainstorm ideas as to what are the causes for this particular effect. That's why this is called the cause and effect diagram. This is the effect or the outcome of all of these different causes. Now, these causes are not necessarily proven. These causes are potential causes for this particular effect that we're experiencing. If you notice down here, I have this color-coded as well. Most cause and effect diagrams don't drive you to color coding these ideas. These are just brainstormed ideas. But I like to color code them to give a little bit of delineation and stratification between the different brainstormed ideas. And the categorization is the red ones are high impact with easy implementation. That means you would have a high impact of fixing this problem, and it's really easy to do. Those are the things that you have got to fix. If you say it's easy and it's a really high impact towards fixing the problem, why haven't you done it yet? That's the question I would ask as a manager. Then the green ones are high impact with difficult or hard implementation. Those are things, if they have high impact, you either need to fix them quickly, immediately, even though it's difficult to do, or you need to have a plan in place to be able to fix those things. If they're low impact with easy implementation, again, if they're easy, why not go ahead and do them? Get that gain and go ahead and make that improvement to the process. And if they're low impact and difficult implementation, then you might not want to do those. The only reason why you would address the things that are in purple would be if you haven't gotten enough gain so that you're meeting your customer requirements or your process requirements that you've laid out for yourself. Okay? Now, how do we know if things are high impact and easy implementation or high impact and difficult implementation, so forth and so on? Or how do we know that all of these different causes actually have any kind of impact whatsoever on this effect? The only way that you could really know is that these would be your X's and this is your Y. And by changing those things, you could look at a before and after type performance when you are doing hypothesis testing. So how do you know that scope change actually would be a high impact to late TSB delivery? Well, you would have different levels of scope change, and you would see if that would give you different levels of late TSB delivery through hypothesis testing. How do you know that due dates not being assigned for specific on-time delivery has a large impact, a high impact on late TSB delivery? Well, you set different levels of due date and how you would change those for your on-time delivery, and you would see if that gives you different levels of performance, but consistent levels of performance based on the due date magnification in the changes, and see if that ends up driving the same amount of change with the late TSB delivery. See if there is good, strong correlation between these causes with this particular effect. That's done primarily by doing certain types of hypothesis testing. Another tool that we have in the technical field, engineering field, and even it's a business tool really, is a house of quality. Another term for this is a quality function deployment. What you have here is these are the different things that you're trying to deliver to your customer. These are the things that are important to your customer, okay? And you rank them here based on the significance, how important they are to your customer, okay? Up here you deliver how are you going to make these things happen, okay? So here's the maximum power output, and your kilowatt ratings has a very direct impact on your maximum power output. But your kilowatt ratings has nothing to do with your availability. It also has nothing to do with your reliability and your long component life. Does your kilowatt rating have anything to do with efficiency? Absolutely. Okay, so you would go through and determine if you have things that you're controlling in your design and manufacturing processes to be able to effectively give the customers what they want. So how do you know if these things directly impact these things? How do you know that your hows directly impact your whats? Okay, you do that again by correlation analysis and hypothesis testing. Same thing here, you look at your hows. How do all of these things impact each other? So if this is your design process or your manufacturing process criteria, if you change one of these, do you need to look and see if that change to this one has impacted this one? If there's correlation between them or high correlation between them, then you absolutely, if you change this one, you will need to look at this one and see how you have impacted that performance. Again, this is correlation matrices, and so to be able to understand that impact, you would have to be able to do hypothesis testing and correlation testing to determine whether you have strong, medium, or weak correlation or relationship between these factors. Again, these are just a couple of examples of what would cause us to use the hypothesis testing and the correlation tools that we're going to be using this semester. Okay. Next thing that we're going to get into is some of the graphical display of data and some of the descriptive statistics. So getting into what are your key performance measures and whether they're below the standards. What are your key performance measures? What matters? How are those things performing? Before you can actually improve a process, you have to know how a process is performing. Those measures of descriptive statistics are the things that will tell you how you are actually performing at the time. They describe a particular process or a product or some type of object that you are using as the object of your study. Okay, so that will conclude this recording for AT 3403. This is part 1 of descriptive stats.